63 light years from Earth, around a star, astronomers have pointed nearly every major telescope on the planet toward for more than 4 decades. A giant planet sat quietly in plain sight for at least 11 years. Not hidden behind some observational blind spot, nobody thought to check. Photographed, repeatedly, by instruments capable of resolving individual planets around other stars. Nobody noticed because it happened to sit almost exactly on top of a much brighter, already known planet in the same system, wrapped in the glow of one of the most extensively studied dust disks in the galaxy. It took 2 separate research teams working independently, using 2 entirely different techniques, stumbling onto it within days of each other in 2026, to finally recognize what had been sitting in their own archives the entire time. One of the astronomers involved put it about as plainly as it can be put. The planet had been playing hide-and-seek with them for over a decade, and only now could they finally say, "Found you." This is the story of Beta Pictoris d, the newest confirmed member of one of the most famous, most heavily observed planetary systems beyond our own, and the story of exactly how a genuine massive planet managed to stay concealed inside decades of astronomical data, right up until 2 independent groups of scientists, chasing entirely different questions, happened to catch it within the same few days of each other. To understand why this particular discovery matters so much, and why it took this long to make, you first need to understand just how thoroughly astronomers have already studied this specific star system, and why that intense scrutiny still wasn't enough to catch everything hiding within it. Beta Pictoris is a young star, roughly 23 million years old, a small fraction of our own sun's age, sitting about 63 light years from Earth. It first became a subject of intense astronomical interest back in 1984, when researchers using the infrared astronomical satellite detected an unusual excess of infrared light coming from the star, evidence of a large amount of orbiting dust. Follow-up ground-based observations that same year produced a direct image of that dust arranged in a vast, flattened disk surrounding the star, one of the very first debris disks ever directly imaged around another star in the history of astronomy. That original 1984 discovery effectively launched Beta Pictoris into its 4-decade role as one of the most closely studied planetary systems in the sky, a natural laboratory scientists have returned to again and again, using increasingly sophisticated instruments, specifically because it offers such a clear, relatively nearby window into how young planetary systems actually form and evolve. Over the following decades, that sustained attention paid off repeatedly. In 2008, astronomers announced the direct imaging of a giant planet within that same debris disk, designated Beta Pictoris b, a discovery that ranks among the very first exoplanets ever directly photographed anywhere in the sky, rather than merely inferred through indirect methods. In 2019, a second planet, Beta Pictoris c, was confirmed through radial velocity measurements detected via the subtle gravitational wobble it induces in its host star, orbiting considerably closer to Beta Pictoris than its sibling planet b. By the early 2020s, Beta Pictoris stood as a rare, genuinely well-mapped multi-planet system, one of the small handful of stars beyond our own sun, where astronomers had directly confirmed more than one orbiting planet through careful, sustained observation. That's the backdrop against which this newest discovery unfolded, and it's worth being clear about just how unlikely it might seem on its face that a third giant planet could still be hiding within a system this extensively documented. But that's exactly what happened. And the way it happened involves 2 completely independent teams of astronomers, pursuing 2 entirely different research questions, who each stumbled onto the same previously unrecognized planet within days of one another. The first team was led by Ben Sutcliffe of the University of Edinburgh and Marcus Bonzo of the European Southern Observatory. According to the European Southern Observatory's own announcement of the discovery, this team was specifically examining Beta Pictoris b, the system's original well-known planet, using the ERIS instrument mounted on the European Southern Observatory's Very Large Telescope in Chile, when they noticed an additional source of light sitting nearby that didn't match anything in the system's existing catalog. Once they identified this unexpected signal as a genuine, distinct object rather than an artifact of their observation, they went back through archived data from an earlier instrument, the spectropolarimetric high-contrast exoplanet research instrument, known as SPHERE, also mounted on the same Very Large Telescope, along with archived imagery captured years earlier by the James Webb Space Telescope's near-infrared camera. What they found, once they knew specifically where and how to look, was striking. The same object appeared in that older archived data as well, stretching back across a combined observational baseline of 11 years. Tracking its position across that entire 11-year span confirmed it wasn't a distant background object, simply appearing to sit near Beta Pictoris by chance. It was gravitationally bound to the star, moving steadily along a genuine orbital path, exactly the signature of a real, physical planet, rather than an unrelated object drifting through the same patch of sky. Jane Birkby, an astronomer at the University of Oxford and a co-author on that team's paper, offered what might be the single most quotable summary of the entire discovery in a statement released alongside the published research. Planet D, it seems, has been playing a game of hide-and-seek with us for over a decade, and only now can we say, found you. She followed that up with an equally direct description of exactly what happened, once the team knew precisely where to search within their own older data. To our joy, out it popped in previous sphere observations. And reflecting on just how long this particular object had gone unnoticed, despite being captured on camera repeatedly, she added simply, "It turns out it was hiding in the data all along." Based on this ground-based analysis, the Sutcliffe and Bons-led team estimated Beta Pictoris D to have a mass of roughly 2, 4 times that of Jupiter, give or take about 0. 6 Jupiter masses with an estimated temperature near 600 Kelvin and an orbital radius of approximately 26 astronomical units from its host star, placing it considerably farther out than either of the system's 2 previously known planets. Marcus Bonse, describing just how faint this newly identified planet actually is compared to its far more famous sibling, noted directly that the new planet is 100 times fainter than Beta Pictoris b, making it, in his words, the faintest exoplanet ever imaged directly from Earth. That alone would have been a genuinely significant discovery on its own. What makes this story considerably more remarkable is that, at almost exactly the same time, working completely independently, an entirely different research team, using an entirely different instrument and an entirely different detection method, arrived at the exact same discovery from a completely different direction. That second team was led by Aidan Gibbs and Jean-Baptiste Ruffio, both researchers at the University of California, San Diego. According to NASA's own official announcement of the discovery, this team wasn't searching for a new planet at all when they made their find. They were using the James Webb Space Telescope's near-infrared spectrograph, specifically its integral field unit, an instrument capable of capturing both a detailed image and a full light spectrum from every single pixel in that image simultaneously, to study the atmosphere of the already well-known Beta Pictoris b, gathering detailed chemical information about a planet astronomers had already confirmed nearly 2 decades earlier. As Gibbs described it directly in NASA's official statement on the discovery, "We weren't looking for a new planet. We were trying to understand one we already knew existed. Then, this telltale signal appeared in the data where we didn't expect it." Specifically, in a region of the data where the team expected to see nothing more than a smooth, relatively featureless spectrum produced by ordinary starlight simply scattering and reflecting off the surrounding dust of the debris disk, they instead found something structured and distinctive, a repeating pattern of peaks and dips arranged like a barcode, a signature scientists immediately recognized as carbon monoxide absorption, a chemical fingerprint commonly found in the atmospheres of giant planets. Because a spectrum reveals not just chemical composition, but also the motion of the object producing it, the research team was also able to extract precise radial velocity information directly from that same signal. Information that, combined with follow-up observations, using Webb's mid-infrared instrument, ultimately confirmed the signal was moving consistently with a genuine physical planet, rather than representing some kind of instrumental artifact or an unrelated feature of the surrounding dust disk. Further analysis of this same spectroscopic signal revealed absorption not just from carbon monoxide, but from methane and water vapor as well, additional chemical fingerprints consistent with a genuine planetary atmosphere. By carefully matching this specific combination of chemical signatures against established atmospheric models, Gibbs and Ruffio's team were able to isolate this newly detected planet's signal from both the overwhelming glare of its host star and the diffuse, scattered light of the surrounding debris disk, arriving at a mass estimate of roughly 2 to 4 Jupiter masses, broadly consistent with the independent estimate produced by the entirely separate Sutcliffe and Bonse-led team working from ground-based imaging alone. Jean-Baptiste Ruffio, reflecting on the sheer amount of information contained within a single carefully analyzed spectrum, offered a comment that captures why this particular discovery method matters so much for the broader field. A spectrum contains an incredible amount of information. That statement isn't simply a nice turn of phrase. It represents a genuinely significant methodological development in the search for planets around other stars, one that NASA's own announcement of the discovery describes directly. This represents the first exoplanet ever confirmed primarily through moderate resolution spectral template. Matching, meaning it was identified specifically by recognizing its unique chemical fingerprint within a spectrum, rather than through the more traditional approach of directly photographing a distinct, isolated point of light in an image. That distinction matters enormously for understanding exactly why Beta Pictoris d managed to remain unnoticed for so long, despite the intense, sustained scrutiny this particular star system has received for more than 4 decades. According to reporting on the discovery, Beta Pictoris d sits within one of the brightest, most extensively studied debris disks known anywhere in the galaxy, and that same dusty disk, rather than simply providing a clear backdrop against which a planet could be easily spotted, actually behaves more like a kind of fog, scattering light from the host star in ways that make picking out a single, faint, embedded object considerably more difficult than it might otherwise be. Compounding that challenge, Beta Pictoris d's position in the sky from Earth's specific vantage point happened to overlap closely with the apparent position of the much brighter, already well-documented Beta Pictoris b, meaning that in image after image collected over more than a decade, this fainter planet's light was effectively masked by its own sibling's considerably brighter glow, hiding in plain sight directly alongside a planet astronomers had already been studying closely for years. Once both research teams had independently confirmed the planet's existence, and once they knew precisely where and how to search, they went back through the broader archive of available observations and found Beta Pictoris d sitting there consistently, in images stretching back to 2014, appearing in data gathered by the Very Large Telescope's SPHERE instrument and later by the James Webb Space Telescope's own near-infrared camera, all without anyone recognizing what they were actually looking at for more than a decade. The findings from both independent teams were ultimately published together in the same issue of the peer-reviewed journal, the Astrophysical Journal Letters. One paper led by Gibbs, describing the spectroscopic detection made using Webb, and a separate companion paper led by Sutcliffe titled directly, and rather fittingly, Direct Imaging Discovery of Giant Exoplanet V Pictoris d, a decade-long game of hide and seek. There's a genuinely important, broader scientific payoff buried within this discovery, one that extends well beyond simply adding a third confirmed planet to an already well-studied system. According to researchers involved in the work, Beta Pictoris's debris disk has long displayed a puzzling, unusually sharp inner edge. A specific structural feature that astronomers had previously proposed might be explained by the gravitational influence of an additional, as yet undiscovered planet, orbiting in roughly that exact location, sculpting and maintaining that sharp boundary through its own steady gravitational pull, in much the same way a planet's gravity is known to carve visible gaps and edges into the ring systems and debris disks surrounding other stars. Beta Pictoris d's newly confirmed position, sitting just inside the inner edge of that same debris disk, exactly matches where researchers had already predicted a planet of roughly this kind should exist, based purely on the disk's observed shape, well before anyone had any direct evidence that such a planet was actually there. Confirming its existence directly effectively closes a long-standing, previously unresolved piece of the puzzle, explaining why Beta Pictoris's debris disk looks the way it does. There's also a broader significance to the specific way this planet was ultimately found, one that reaches beyond the single star system entirely. Because Gibbs and Ruffio's team succeeded in identifying Beta Pictoris d primarily through its unique spectroscopic chemical signature, rather than through the more traditional method of directly photographing a distinct point of light, their approach demonstrates a genuinely new pathway for finding planets that might otherwise remain permanently hidden within the glare of their host star or the scattered light of a surrounding dust disk, exactly the kind of challenging observational environment that has likely caused astronomers to overlook other similarly faint planets in other well-studied systems throughout the galaxy. As Gibbs put it directly in NASA's own statement on the discovery, this discovery adds another piece to an already fascinating planetary system, before adding a broader reflection on the significance of the technique itself. Beta Pictoris has long served as a laboratory for understanding how planetary systems form and evolve, and now we have another planet helping us tell that story. It's worth being precise about exactly how rare it is for a planetary system to have 3 separate planets confirmed through direct imaging or direct spectroscopic detection, rather than through indirect methods like transits or radial velocity measurements alone. According to the research team's own published findings, Beta Pictoris is now only the second known planetary system anywhere in the galaxy, confirmed to host at least 3 planets detected through this kind of direct method, following the previously established HR 8799 system, whose 4 directly imaged planets have made it one of the most celebrated multi-planet discoveries of the past 2 decades. Joining that extremely short, exclusive list places Beta Pictoris in genuinely rarefied scientific company, and it does so specifically because 2 separate teams of researchers, pursuing 2 entirely different scientific questions using 2 entirely different instruments and techniques, happen to stumble onto the same previously overlooked object within days of one another in what can only be described as a remarkable and entirely unplanned convergence of independent scientific effort. There's something worth sitting with in the sheer improbability of that timing. Neither team set out specifically hoping to discover a new planet around Beta Pictoris. The Sutcliffe and Bonslet team was examining the already known planet B using a specific ground-based instrument, chasing down what initially looked like nothing more than an unexpected, unexplained source of light nearby. The Gibbs and Ruffio-led team was independently studying that same known planet's atmospheric chemistry using an entirely different space-based instrument, looking for detailed information about a world they already understood reasonably well, only to stumble across a chemical signature appearing in a part of their data where they had specifically expected to see nothing notable at all. Both teams, working in parallel, entirely unaware of what the other was finding at almost exactly the same moment, arrived at the same underlying conclusion. A third giant planet, hiding for more than a decade in plain view, embedded in one of the most closely studied dust disks in the entire galaxy. That kind of quiet, accidental convergence, two independent teams catching the same previously invisible object within days of each other, purely by chance, while each pursuing an entirely unrelated research goal, says something genuinely important about how much valuable scientific information can remain locked away inside data that's already been collected, sitting in archives, waiting for someone to look at it in exactly the right way or ask exactly the right question of it before its significance becomes clear. Beta Pictoris D wasn't a new observation. It was an old one, finally recognized for what it actually was, more than a decade after it had first been unknowingly photographed. It's worth reflecting, too, on just how much this particular discovery illustrates about the current state of exoplanet science more broadly. Astronomers have now confirmed nearly 6,000 planets orbiting other stars, the overwhelming majority found through indirect methods like the transit technique or radial velocity measurements, rather than through directly imaging or directly detecting a planet's own light or its own atmospheric chemistry. Direct detection, whether through imaging or through spectroscopy of the kind used to confirm Beta Pictoris D, remains genuinely difficult and comparatively rare, precisely because planets are so overwhelmingly faint compared to the stars they orbit, and because dust, debris, and the simple, practical challenge of separating a planet's faint signal from its star's overwhelming glare continues to limit what astronomers can actually confirm directly, even using the most advanced instruments currently available. Every new direct detection, especially one achieved through a genuinely novel technique like spectroscopic template matching, expands the practical toolkit available to researchers hunting for planets in exactly this kind of challenging, dust-obscured environments that are common throughout the galaxy, particularly around young, still-forming planetary systems, not unlike Beta Pictoris itself. Beta Pictoris D sits there right now, roughly 26 astronomical units from its host star, a gas giant a little over twice the mass of Jupiter, quietly completing its slow orbit within the same debris disk astronomers first photographed more than 4 decades ago in 1984, the very observation that first turned this particular star into one of the most closely watched objects in the night sky. For at least 11 of those years, this same planet had already been captured repeatedly by some of the most capable telescopes and instruments humanity has ever built, sitting directly alongside its already famous sibling planet, hidden not by distance or faintness alone, but by the simple, almost anticlimactic fact that nobody had yet looked at the data in quite the right way to notice it was there at all. If you want to see what else might still be hiding inside decades of archived data from some of astronomy's most familiar, most thoroughly studied star systems, this discovery is a genuine reminder that the search is far from over. Subscribe if you'd like to keep following where it goes next.